Okay, so hello everybody. I don't see you, but I'm sure you're there. Um, and I'm happy for those who are here to talk about parallel I/O. Today, I will first do a presentation, which should be about 30 to 45 minutes, and then Sean will add a few things. In the end, he will show a little bit material more related to visualization. So first, there will be an introduction where I will talk about Scratch, then the Lustre file system, then talk about common approaches in parallel I/O, and then gives a few general recommendations. And then the second part, there will be real fun stuff that I was really excited to prepare that in these past days for you, these examples. And it's ADIOS 2. It's a recent parallel I/O library, and we will see how we can do much more than just writing to the file system with this. Okay, so introduction. Um, well, if you go on the internet and you search what is a Lustre file system, right, which you're supposed to have here, you find this, and probably it doesn't tell you a lot. So I'll just give here an overview of what it is. We have here on the left the Lustre clients, so called, which are in our case here just the compute nodes. Then we have metadata servers, which are just somewhere connected. Um, and then we have object storage targets, in short OSTs. And so these OSTs, let's say, are the most important for us to think about. There is actually the stuff is written, yeah. And the metadata, well, is the metadata. And so, yeah, on this in these object storage targets, there we have enormous amount of hard disks. Now, when you look at the environment variable Scratch which you have on Daint, then you see this here, and there it says SNX 3000. So just to know that what it is, this is a Cray Connection 3000. It's the hardware, and this can achieve a peak performance of more than 100 gigabytes per second. Uh, but of course, only when you write in parallel. So it means you need to write in parallel to the all the 40 OSTs in order to be able to get such a performance. So now common approaches. Yeah, the typical approaches is either file per process, where the green points here are processes. Yeah, in this case we have here 4 processes. So when you have file per process approach, each process writes his own file. In the shared file approach, everybody writes the same file. And so when you have a file per process approach, the files automatically get on different OSTs. So you automatically use, in this case, 4 OSTs. However, in the shared file approach, in this case, the file just goes on one OST, so you use only one of them. So it's not parallel in the end, right? The actual writing to the disks. And so if you want to write that way on multiple OSTs, you need what's called data striping. And so it means just that you write a part of the file on the first OSTs, another part on the second, and third on the fourth, and so on. Yeah. So in this case, you would have a stripe count of 4. Yeah. It means we distribute the file on 4 OSTs. Now the pros and cons of these approaches. So the file per process, well, it kind of gets simpler than doing this. You don't need any IO library. You can just uh, use the language's standard mechanism to write on the disk, and that's it. Now, the bad point is this creates enormous amount of files if you use it at large scale. Also, then typically you will get maybe one file even per time step if you have a simulation with time steps. And so you can really get a lot of files, and this is not good because it brings down the file system as you risk to get the contention of the metadata service. So general recommendations here: set the stripe count to 1, and this is the default. That's the good thing. Don't create thousands of files in a single folder. Don't access thousands of files simultaneously. And uh, as I said before, if you do something very bad here, everybody suffers, not only you. Uh, and then in general, at the very small scale, stripe count bigger than 1 might be better, yeah. But this is not really important. Now, the shared file approach, if you use striping here, so keeping the number of files small is straightforward. So that's very good. Post-processing is very simple, as with you can use common tools and IO libraries. Uh, sorry, you can use common tools because the IO libraries, they make it easy to add extensive metadata to your data, and you can create a shared file in a way as if it was written by a single process. So you can easily read it afterwards from a single process. While if you write out in the previous approach, if you write out so many files, then and then you want to read it with a different amount of process, it is quite difficult. Yeah? Then a negative point is, yeah, it requires careful tuning very often in order to reach a good performance. Uh, Many people say IO is black magic, right? So that says it all. Now, general recommendations here. So if you access one large file, one large shared file, then set the stripe count to number of OSTs. So this way you can write in parallel on all of the OSTs. Yeah. Then if you simultaneously access multiple large shared files, then set the stripe count such that, well, the number of files times the stripe count is a multiple of the number of OSTs. Yeah? So a multiple of 40 here. And uh, this multiple of the number of OSTs is like between 1 and 4 to get a good performance. This is just by experience. And well, now nevertheless here it can also be better to use maybe only 32 OSTs because some OSTs are already overloaded by other users, etc., or it can be at a better alignment when you write these stripes, etc. And then in general, for any small file, it does make sense to split it in parts and write it on different OSTs, right? So there you just set stripe count equal 1. Now, the next recommendations, it's convenient to set the striping configuration for your simulation output folder, for example, like this here. So you do LFS, set stripe count, and then the folder, yeah, the folder where the output of your simulations goes in. Yeah? And so automatically the files which are created will get will use this configuration, the striping configuration. that was defined for the folder. And but attention, don't copy your executables in there, because as you have also the executable split over all the OSTs, and then the startup time, etc., can get long. It doesn't make sense, right? Um, then check the striping configuration with this command, and of course you can get help like this to see all the functionality. Now we get to the next topic. This is collective I/O operations. So they enable the merging of I/O requests from different processes into a fewer requests, which are bigger, and so this can improve performance in general. And so here, for example, you got 4 processes, and instead of that each of them would write his stripe. Now this sorry, this here would send his data to this guy, and only this guy would write, yeah. And this here would send his data to this guy, and this guy would write. So only 2 of the 4 would write here. And then here you can see how you do that in MPIO, HD5, NetCDF. And now in this particular example, just to be clear, we would have here a stripe count of 2, yeah, and we would so write on 2 OSTs. And by default, the aggregators are equal to the number of the stripe count, and you can change this, for example, like this. With this MPI hints, they're called. So you would call CB node, which means collective buffering nodes. You would set it to 64, for example, yeah. Then next recommendation. So print the used MPI/IO hints, as I just said. For example, CB nodes, you can see. And this is also useful when you use HC5 or NetCDF, as they use MPI/IO underneath. Yeah, so this is useful for all of these libraries. And this is the way how you make it printed. Yeah, and also you can get some statistics. And then if you want to know more about these hints, etc., you can do it with this man page. You can get it. Then, of course, there's extensive documentation for these libraries, which exists an enormous amount of time, HD5 and SCDF. So go there to see how each of them is best used, right? And also, it is good to adopt metadata conventions for your field uh, in order to simplify pre and post processing. And here you get to have some examples of some of these conventions. Now on Piz Daint we have the following libraries available. So create HC5 parallel, create NetCDF HC5 parallel. This is NetCDF using HD5 underneath. And then this one, which is NetCDF using pNetCDF underneath. In general, with HD5, it's kind of more stable. It's a bigger development, yeah, than pNetCDF. More funding. All right, then some general recommendations. Really don't use ASCII, right, for writing out all your data, except for some small parameter file for really for small things, but certainly not to write out all your floating point numbers. This This is extremely slow. Avoid opening and closing files frequently. Just open your files once and then the very end of the simulation close it, right? Then do not open files for read and write access, but instead just for read only or write only. Avoid small and frequent high requests. And this is very important. You should group your, for example, you don't make a loop over your array and write out each of the floating point numbers separately, but instead um, uh, you use a function which allows to specify a whole buffer with a certain length, to write your whole array with one request. You think it doesn't matter, but it does. The the all the libraries, etc. What is happening behind is not that smart in the end. Then avoid random file access. Irregular access patterns work best in general. Avoid also that multiple process access really the same data, because uh, then you get a blocking situation there, right? Read the very small files just from one process and broadcast to the other. But this for example is in, of course, if you do it really more like by hand, you can also use parallel IO, which libraries which would do that without you even knowing it, right? And at the next part, when I talk about the ADIOS, you will see these kind of things you don't have to care about then. And then this is a detail, and in general, really be aware that if you cause contention on the file system, all users will suffer, because this where you write to, this is shared with all the thousands of users we have. Okay, now comes the fun stuff, and so I say, how about we say adios to most of that stuff, huh? And we just let some experts take care of that. We just want to declare what we want to do. What do we not like? Declare in a general way. I want to do this and that, but I don't want to have to think about that I write first, that I send some stuff to another process, and this one will write, etc. No, I just want to say what I want to do, right? And experts take care of the details. So ADIOS2 is a very recent library, and it is so much more than just writing in parallel to the file system. You can see here, this is an image from their documentation, ADIOS2 documentation. And so this is basically Piz Daint, say. And then ADIOS even allows you to write to cloud storage directly via different interfaces, different protocols. And here to some analytics site, collaborator site. It's really, they try to come up with a solution for really the whole scientific workflow with collaborators, etc. Yeah. Now, we today will only look at this part. Yeah, we're only about Piz Daint. I mean, not all, also not every scientist use cloud storage, etc. in that way. Yeah, so we focus on this, and yeah, this is really not an attempt to give a complete overview of the ADIOS2 features. Also, not for this part itself, because ADIOS has so many things that it can do. All right, so I say it's much more than file I/O. It enables a variety of data staging scenarios for in-situ visualization, monitoring, or analysis. So you can stage the data for uh, visualization or something on the same nodes, or different nodes, or even on external machine, as we just said before, but we'll not look at that. Yeah. And you can also do on the fly some lossy or lossless compression. Just very easy, you will see that. It is super highly declarative. So we let the experts take care of detail, as I said before. It is a unified, it has a unified API for file IO and data staging. So you write one code, and with a little switch in a configuration file, we change one entry, and instead of writing to file, it will write, it will send the data to another node, and there you can do visualization. We will see that. Then there are bindings available for C, C++, Fortran, Python, and it doesn't matter if you have your simulation in C, C++, for example, but then on the other end, you get the data um, with Python, for example, to do your analysis or visualization. This is completely interoperable. And yeah, this is a project with a big funding. It's from the United States Department of Energy. It's called the Exascale Computing Project, where it is part of. All right. So what kind of approach is this ADIOS 2 now here? We saw before file per process, or oops, or a shared file, and it is neither of them. You know, it is a bit an unconventional approach, and so it is rather what I would call a file per aggregator approach. So it does send. It's not each of the processes writes a file, but so for example, when we have 4 processes, only 2 will write, but they will write the whole file and not a stripe like in this approach here. Yeah. And this makes it also easier, let's say, to optimize I/O, because you just have one free parameter, which is the number of aggregators, and it avoids a lot of complexity. And when you write in the same file, then alignment and things start to be important. So it makes it easier to have a better performance, I believe. And then ADIOS, so is ADIOS dataset is rather is actually a folder and not a file. You know. Now the design of ADIOS 2. So this looks maybe a bit scary at the very beginning, but it's basically all you need to know and have in mind. So here in red, you see the 3 main components here. This ADIOS principal component here is just to initialize the library, to pass the configuration file I already mentioned, the MPI communicator, and that's more or less it. Yeah. Then we have the I/O component, which where you declare a lot how the uh, what kind of stuff you want to do. You want to create a variable, uh, add some attributes, etc. And then we have the engine, um, which is it's like engine motor, right? It's the thing that actually then does the work. And so here the engine will take care of actually writing stuff and reading stuff. Yeah? And then, so in addition to this, we have a variable, which is, yeah, for example, temperature or whatever that you would create. And then we have one last thing, the operator, which is nothing else than something that allows to add some on-the-fly lossy or lossless compression. And so these component names are important because we use them also in the examples for clarity. Yeah? Okay, so I told you before at the beginning, it was really fun and exciting to prepare these examples because I think it's really awesome, really amazing what you can do here. I created a super simple 2D heat diffusion example. So it is an MPI code in Python. I didn't do it in C or C++ because, or Fortran, because it's just easier in Python, right? It's only for demonstration. But it uh, could well have been in C or C++ and the visualization in Python, yeah? But so both are now in Python. The simulation and the visualization. And so this allows to look at how to access the file system in parallel, selecting different file formats, including the compression and stage simulation output for visualization in situ. And so this contains, of, as I said, of an MPI Python file, then a visualization file, which is a notebook, so it can be run in Jupyter Lab. This is very exciting because then you can directly interact and see uh, your visualization without having to do some complicated port forwarding things with an approach where when you would call things from terminal, right? And the third thing is this configuration file. This example, you can find it here. And really, if you want to get into ADIOS, I think it is a nice way to get started. Now, so we'll go through these different things here, yeah, that I just mentioned. So how you write with ADIOS, the file system. So we initialize the components, ADIOS, IO, and engine. These are the main components I mentioned before. And we declare the variable temperature. So here you see here how you initialize it, and you pass it the configuration file. Then we declare an IO, which we call here writer IO because here we define how we write the stuff. Then we create the engine, which, as I mentioned before, says how actually we write things concretely, and so or what we do concretely with it. So we do write, and here we specify the file name, and yeah, and then to create the temperature, we use this IO again, define variable temperature, and here we pass the array T temperature, the global size of this variable, then the local size of the variable in this very process, and where it starts in where this local part of the variable of this process starts in the global problem, yeah? And that's it. Because you always need to say, okay, here I have my process. I have this little part that I have in the global problem. And so I need to say how big it is and where it is. And so what I'm showing here is directly extracted from this example here, right? So you can see it afterwards in detail. It's exactly the same code. It's really a working code. Yeah, it's not something more or less. All right. So then afterwards in the simulation, the heat diffusion simulation, we have a time loop where we write, in this case, n steps times during the whole simulation. So here 50 times I chose, and this is achieved with this modulus expression, which ensures that it doesn't write every time step, but only every now and then, and in occurrence just as many times that in the end we get 50 outputs. And now here you see the essential thing about how to write something concretely, right? So we say we have a step, we begin a step, then we put all the variables we want to write, temperature, pressure, whatever. Yeah, in this case only temperature, but in other cases you'd have more things. You will declare all this. I want to write all this in one time step or iteration step or whatever it is. It's just a step for ADIOS. And then we have an end step. And only actually in the end step, ADIOS will start to write when it already knows all you want to do, right? It will not start immediately writing out stuff, etc. Only when you call end step, then it will, in an optimized manner, do all the stuff you said it should do. All right, and then so in the rest of this time step, we will do the actual 2D heat diffusion simulation, which you can see in the concrete example. In the end, we close the engine. Now the third thing is we have the ADIOS XML file, which is the configuration file. And so here we specify IO, writer IO. Yeah, this is the thing that we had here before. We had here declared the writer IO, which is what we want to use. So here we specify the details of the writer IO. So we say the engine that it uses is an engine that writes files of type BP4, which is the standard file type of ADIOS 2. And so here, for example, we can say now substreams are 128. So it means it will write 128 subfiles instead of, yeah, not instead of, just it will write 128 subfiles like that. If you have, let's say, 1000 processes, it will send this stuff to 128 of them and they will write the stuff. Yeah. Now, if you use less process, if you use only 4, let's say, then they will write only 4 files and not 128. This is automatically adjusted. All right, so we saw basically the 3 components, right, to writing. So we had the initialization of the stuff. No, sorry. The initialization of the stuff, the declaration of the steps, what we do, and the configuration file. Now we have the same 3 things for reading as well. The initialization, which is basically the same as writing, just instead of writer IO, I have reader IO. Instead of write, you have read, and that's it. Now here is a detail. as we use this from Jupyter Notebook where we don't have MPI, we don't have the MPI communicator, and we actually use the serial version of the ADIOS library here. Then, so as I said, first thing is the initialization. The second thing now is a loop where we have again begin step, get, end step. Before, the last time I had put, here it's now get. But it's the same idea. We start a step, we say everything we want to get, temperature, pressure, and whatever, and then we end step. And only in the end step it will actually do the stuff that we declare we want to do. And then we close, right? Now, what is a bit different is, well, in the actual simulation, we have a time loop. We say NT time step we want to do. But here, on this side, on the reader side, we don't know how many time steps there will be a priori. We're just listening. We're waiting to see how many steps are coming in. So that's why we have here a while loop and not a for loop. And so while there are steps coming in, we will visualize it, yeah. And one important little nasty detail. So this TID here, this inquire variable, cannot be inside of this if statement. Then you get a weird error, which is hard to debug, which the guys, the developer, helped me to find. And so I thank also to these guys from ORNL and the SST developer from GA Tech or something. They helped me with that. Yeah. So where was it? Okay, so this TID cannot be inside of this if statement because then it becomes invalid after a few time steps. So even though our temperature has a fixed size, this must be done every time step. Also, another thing, you cannot inquire this even, let's say, before the first step. You have to do everything inside the step before it's not there. It's not, nothing exists before a step. All right, then, so the third thing, so we had, as again, initialization, the loop, and now the third thing, the configuration file. So now instead of writer IO, we have reader IO, and the rest is the same. Okay, so I showed you the essential thing, how we can access the file system in parallel. Now, I'll show you how you change, for example, to HDF5. You want to write HDF5 and not BP4. Well, it is that simple. You change the engine type to HDF5 and you get the HDF5 file. That's it. For me, this is really incredible. Yeah. But now it gets even more awesome. Now, you want to do an in-situ simulation. You don't want to write an in-situ visualization. You don't want to write to the hard disk at all. You just want to have your simulation, send your stuff to some other nodes, and they will do all the in-situ directly a visualization or analysis or whatever of this stuff. That's how you do it. You just change this to SST and you're done. So you have one single code to declare what you write and read, and then you can switch here between different file formats, and even you can switch to data staging. And so now to the last topic here of ADIOS. And it's also another absolutely awesome feature. You can very easily specify for your different variables. For example, here temperature. You can specify what kind of compression algorithm you want to use just by adding it to your configuration file. You don't need to change the code ever. You can do most of these things also without configuration file, just as a side note, um, in the code. But to me, it's much nicer to have this completely separated. And I think also they invented that because it makes more sense. Yeah. Okay, so you can specify, for example, for the variable temperature, I want to use the set compression algorithm, which is a lossy compression algorithm. And I specify I want to use this accuracy. So I put an error bound for my lossy compression. So it will be sure that even though I use a lossy compression, the error will never be bigger than this. And so this is, I guess, for visualization and many tasks, that's just good enough. And you can get maybe like 100 times compression and things like that. Yeah. You can also do lossless compression, and but that didn't show here. Yeah? All right, so now I get to some demos I prepared, where I show you this actual example from which I show the snippets now working in action. Yeah. So I will run it and always stop. Yeah, I'll leave it like that. So I will run the demo and stop when there's something interesting. Yeah. So here you see my terminal. I type ls. You see what we have here. As I said, we have the configuration file. We have the visualization notebook, and we have the MPI diffusion simulation code. Here in addition, we have another little notebook which uses another way to do the same thing, but I don't want to talk about this here today. So we don't care about this one, yeah. Only the three that I said before. This one, and this one. All right. So I ran the code. You see here with 4 processes. I ran the MPI code. So it allocated the resources. Oops. Oh, now I did something wrong. I cannot scroll, of course, here. Sorry, I need to go back. All right, so it ran the whole thing. You see the outputs. It does, for example, an output that's time step 5,200 and at 5,400, etc. And then we see here below now it has created this file, diffusion2d.bp. Now I'm showing the size of it. It's 25 megabytes, very small. Just a little comment. If you do write some big files, of course you cannot do here on the home like I did. You need to do it on Scratch. This is really because it's super small that I did it here. Then the next thing you see here, the content. You see the content of this file. So you see inside there are actually 4 files: data 0, data 1, data 2, data 3. And there are some metadata files. Oh, and one more thing, and you see together this these files, these data files, they make up this 23 megabytes. Yeah, if you sum this amount of megabytes that they use. Now BPLS is a little tool that comes with the ADIOS library that allows you to investigate your variables. And so you could see here, oops, sorry. No, sorry, I wanted to stop earlier. Yeah, so you can see here, it is of type double. The variable is called temperature. We have 50 time steps, and the size is 252 by 252. It is not 256 because of the halo has been removed here to make the global thing. And now here the last thing, you can see all this. Actually, it says here step 344 up to 59, up to 49, because we have 50 steps that were written. And in addition, you see we have block 0 to 4. This is because of we wrote 4 subfiles, 4 substreams. So you can that way understand the whole output. All right, so that was the first demo. Now here you can see the second one, oops, which is the reading of this file that we just created from the Jupyter notebook. So we import some stuff, then we do the initialization, and you see with the engine type, you see it's a BP4 reader. Then afterwards, we do available variables, and you can see there are 50 steps available, the maximum, the minimum, etc., the shape of the problem, etc. So you get all this information, and then afterwards, we do now the visualization of the whole thing. So we have, as I showed before, the while loop. So while we get new steps, we visualize stuff. Okay, so enough for this. You can look in detail afterwards for the rest, because I will now go a little bit faster because we need to pass over to Sean afterwards, especially as we started a bit later. So you can see here now the coolest thing, right? Now here we have the terminal on the right, Jupyter Lab on the left, and here we start. On the right, you see we have okay, nothing yet, just the files. On the left now, I change the type of the engine to SST for both reader and writer. Then on the right, I run the MPI simulation. It is running. And you can see it created this .sst file. If you look at it, if you cut what is inside, it is basically nothing. It is just some information to connect. So this allows here on the left the Jupyter notebook to connect. And so here it connected. It says the engine type is now SST reader. Then if you go to the available variables, it says there's nothing. Because now in this mode, you have nothing before you started to read in some steps. You're just blind. You're waiting. You have to wait. You just read step by step. You know nothing more than the current step. Yeah. And so then now we run the visualization, and you will see it does exactly the same visualization as before. But now it is streaming the data directly from the nodes where the MPI simulation happens to the node where the Jupyter Lab is running. Yeah, so and it goes to 49 steps here, and that's it. Now I get to the last. Oh yeah, one last thing, and now in the end it will automatically remove this SST.sst file. So now I get to the last demo, which is again the right terminal, on the left in Jupyter Lab. And so here I didn't talk about this thing before. So we have rendezvous reader count. It means the reader here, the Jupyter Lab this is the writer. The writer waits until one reader is connected. And it has a queue of 5 steps. And when they are full, this is a buffer, and when the buffer is full, it will block. It will not continue the simulation. You will see this behavior now, right now. So you see now, on the right, I run the simulation. I run it now just on one node to see very nicely the blocking. Yeah. Right now it's blocked. You see, it's blocked because the reader hasn't started. Now it's waiting for the reader. Now the reader connected. The reader connected, and now it is blocking here after 5 steps. It filled this buffer. It's blocking. Until the steps are not consumed, it will not continue here. All right. And now as soon as we start here with the consummation of these steps and visualization, you see on the right, it continues. So to me, this is absolutely awesome that we can do so many things with so little code. All right. That's it. Okay, so I'll just quickly go back and then give over to Sean. Where? Ah, it's here. Okay, so I don't have much conclusion here because, yeah. So parallel IO library doesn't mean good performance. You need to do careful tuning with traditional libraries. IO should help you to get a better performance without doing so many things. And ADIOS is really, for me, an amazing thing with all that I just showed you. Thank you very much. And so I give over to Sean.
Thank you, Samuel. Perhaps we should allow some time for questions if people want to, until I switch to my desk.
Any questions from the live audience? I think, Sam, you can stop sharing the screen so that
Okay.
John can take over. I don't see any hands raised, so I think you can start.
Okay, I will continue. So thanks a lot, Samuel. I must say that I was very excited to work with ADIOS and with the initial demonstration that Samuel has put together. This is very, very exciting. I'm going to take a step back and talk about parallel I/O for scientific visualization. Presumably, if you're doing parallel I/O, it means that you're doing some big data uh, simulation, because otherwise, I mean, you'd be uh, you'd be going with a simple solution. If you have big data, you also presumably uh, want to do visualization in parallel. Now, very often times there's a big difference between the number of compute nodes that you allocate for your simulation and the number of compute nodes you allocate for your visualization. Usually, I mean, a good rule of thumb is that we can actually handle close to 100,000, no, I'm sorry, 100 million cells for a grid on a single compute node. So parallel I/O for parallel visualization would apply if you are in the range of several hundreds of millions of cells. There. Now, uh, let me go on. So doing parallel visualization involves, in any case, as the first step, doing parallel I/O. But you need to understand what type of data grid you have. Now, if I look at the data, the VTK data model, which is pretty common amongst the visualization applications, for example, at CSCS, we have Visit and ParaView, which both use the VTK library underneath. That VTK data model includes the following grid types, which are most often used. The VTK polydata, which is used for geometry, and this often doesn't really play very nicely with parallel I/O. There are some exceptions, however. The second type of grids are the regular grids, the structured grids. And in VTK, we have the VTK structured grid, which is also often called a curvilinear grid. We have the rectilinear grid, which are very often used, for example, in atmospheric science, climate, weather, etc. And then we have the image data, which is the really completely irregular Cartesian grid. And these type of grids play very nicely with parallel I/O and parallel visualization. So if you have in your simulation those particular configurations, then you are more or less all set for parallel visualization. You also have the so-called VTK unstructured grid, which is anything doing with finite elements, for example, type of simulations, and then the VTK molecule mesh type, which can also play very nicely for parallel visualization. So if you have, for example, some very large molecular data, you'd have to speak with me. I know there is an existing solution to do things in parallel. And then the last type of data organization that is probably worth mentioning is the so-called multi-block data set and the hierarchical box data set. Those would be often found when we have collections of the grids which I have named above, the structured grids, the rectilinear grids, and the image data. For example, in adaptive mesh refinement, we would have collections of VTK image data. Or else, if we have an octree-based adaptive mesh resolution, we would have a collection of unstructured grids of type voxels. In any case, in the case of those collections of grids, then the parallelization would happen at the grid level. Okay, instead of splitting a single grid among multiple compute servers, we would split the collection among the parallel servers. Now, of course, there are many data readers in both Visit and ParaView. We have over almost, I think, 200 different readers, which are standard in the distribution, but not all of them are capable of reading data in parallel. So you have to be pretty careful with that. And to understand how the splitting, the load balancing of data would be done if you use a data format that supports parallelism, I think we first have to take a quick look at how a parallel visualization pipeline works. So I have the next three slides here to explain a little bit how both the Visit and the ParaView engine work in parallel. Now, the standard definition of a visualization pipeline is really a connection between multiple modules. Of course, you have the I/O module, which do the reading of the data, be it from disk or from a stream, as Samuel has introduced before me. And then you have multiple filters. If you take, for example, a 3D grid, a typical filter would be an isosurface computation. And then you finally have the image generation. Now, this pipeline made of a data source and then multiple filters operates with three different passes. And the first pass is something which takes very little computation, is in the ParaView language, is called the update information pass. It's basically a pass where the source of the data readers, advertise what is the global regions of data that can be read. I have an example here in a few slides. Typically, the data reader would say there is a grid available with a resolution of, for example, 2000 cube data points. Or if you are dealing with particles, you would say, I have 100 million particles of type gas. I have 100 million particles of type halo, etc. If you were dealing with molecules, you would say, I have so many atoms available, so many molecules there. But it doesn't mean that the pipeline actually initiates reading the data. This is only a pass that informs the engines what is the global regions of space that can be processed. Then the second step, let's see, I see there's some confusion in my slide. No, this is correct. I'm sorry. So the second pass is where the parallel engine computes what each portion of which each server should process. So if I take again the example of the grid of 2000 of resolution 2000 cube, if I have 8 servers, that second pass of the visualization pipeline would decide that each compute server takes charge of a subset of the grid. if we are dealing, for example, with an unstructured grid made of so many tetrahedra or hexahedra cell, again, we would split the mesh in so many parts. Now, of course, this goes back, the question about splitting the data goes back to the question of the parallel I/O and the data format that is used. If the data format that you use supports splitting and reading subsets of data, then this parallel visualization process can indeed function in parallel. So once this is decided, the information about the responsibility of each server goes back to the source, and the final pass, the third pass, is actually the pass where each compute server reads its data and the filtering takes place. So in parallel, we basically have all those different, we have a replication of the visualization pipeline on each compute server, and the I/O takes place in parallel based on the resources available. Now, you might have to do some ghost cell generation, some exchange of data between the filters. And also at the reader level, if your parallel reader needs to exchange information between each compute server, this can also be done at that point. So there's the example that I was mentioning earlier. The very first pass would advertise that a grid of 2000 cube is available. The second pass would say, okay, I have 8 compute nodes available with one task. I divide the global scene by 8, and each of the chunk is a chunk of 1024 cube, and each task will read those data in parallel. Now, if you recall the discussion by Samuel about file striping, etc., if your file is organized, your file or your collection of files, okay, here the reading of the data does not necessarily imply that you have a single file. You can have a distributed solution among multiple files. And the nice thing about both visit and visit, this computation of the subset is done automatically. So that's really the a nice feature. Now we need to talk about metadata convention, and I know Samuel already has mentioned that very quickly. Some file formats, for example, the most common we have here in use at CSCS, HDF5, NetCDF, ADIOS, they define the data sets, groups, they define a way of arrange data, but it leaves really complete freedom to the users about their internal organization. For the people familiar with HDF5, I could store an HDF5 data set with any name I want, with any attributes I want, and I could place that data set anywhere in the file. That's not really good, because the next person coming after me, the consumer of the data, doesn't know how I have organized my data. So the example I usually use is, it's just like using the English vocabulary, but without proper grammar and proper syntax. What if I were to put all those words together in English? Dog, cats, nearby, fights. You wouldn't make sense. You wouldn't know how to make sense of this sentence, because it's not a sentence, in fact. The proper convention would be to put the article before the noun, before the verb, etc. So the real phrase would be, the dog fights with 2 cats in the nearby field. I think I made the point. The point is that if people agree on an organization of the elements of your vocabulary, then you can make sense of the data. So that's what the metadata conventions are. Okay. There's the very well-known convention for the climate community is, for example, the CF convention. You can click on that link and go directly to their website. The CF convention really is a way to organize climate and forecast data in a proper way, such that both the data producers and the data consumers agree on an adopted standard. HJ5 also has the same, yeah, what I forgot to mention is that, I guess, yes, the CF convention is based on the NetCDF API. Similarly with ADIOS, similarly with HJ5, we have conventions. One of them is the Gadget2 format for this astrophysics code, which originated at MPI Garking. This data format using called Gadget2 is a standard format, and based on those conventions, people can write a parallel data I/O interface. So this is what I have done for ParaView, for example, at CSCS. An alternative to using an HJ5 convention is the XDMF format. So suppose that you have an existing code, a legacy application that already uses HJ5, but it doesn't have. It came about before the adoption of those conventions. You can still read your data in parallel. In some cases, we will see about that using the XDMF format. So again, here I recommend that you visit this particular website, www.xdmf.org, where this is explained. Basically, XDMF is a split of the data description. The data description is something about the number type, the precision, the locations, the rank, the dimensions of the grid, all of this which are independent of the real size of the data. So this is what XDMF refers to as the light data. And then the heavy data, the heavy numeric data is stored in HJ5 itself. Now, the light data is very small data, which is usually user readable. It's ASCII, it's written in XML. So it's very easy to share. And this is exactly this light data information, the metadata conventions, which are used for the parallel I/O to decide on how to split data between multiple compute nodes. And once the splitting has been decided, only then the heavy data is loaded by ParaView or visit in parallel. There. So in HDF5 vocabulary, we usually talk about hyperslabs. I forgot if ADIOS is actually using the same word for a chunk of data, but basically the visualization servers would read sub-pieces. In some cases, they can be HDF5 hyperslabs of a data set, or they can be ADIOS subsets of a particular numerical array in any dimensions. Now, if I take just, even though it seems like parallel visualization using parallel I/O would be something trivial and ubiquitous, if I take just 4 different examples here from the ParaView experience I have, we would see that actually 3 out of those 4 data formats do not support parallelism. So you have really to be very careful with that. How would you know that a particular data format is not being read in parallel? Well, if you look at your ParaView memory consumption, you would see a strong imbalance here, as we see on the right side of my grid. a strong memory imbalance. And then if we look at the variable called process ID, you would have a single color showing the grid allocation among your compute servers. If I take now another example using the same data with a format that supports parallel I/O, then I would have a very ideally load balanced situation here. Here I'm using 4 processors, and I can see that my volume is split among pieces, among 4 different pieces which are of equal weight. Now, of course, doing parallel I/O and parallel visualization also means that in some cases you would have to support ghost cell generation. Okay, so I hope this is something, this is a concept that is very clear to all of you. If you're doing a parallel simulation, you have a grid or a set of particles which are split among multiple compute servers. When you do your parallel I/O, in most cases, you do not save the ghost information into the file format because it allows you to do a restart, a checkpoint restart, using, for example, a different number of nodes. So ghost zones are usually recomputed at a restart. The same thing happens with parallel visualization. Ghost zones are recomputed on the fly based on the need of the visualization pipeline. Now, among the parallel I/O plugins that were developed at CSCS in the last few years, I can advertise a parallel NEC 5000 reader, a parallel reader for the Parasol solvers, and then also the Gadget 2 HJ5 reader, which we mentioned earlier. So if you are interested by any of those solvers, you need to talk to me. The fact is those readers are developed as independent plugins. So they're not distributed in the same fashion as the regular application. In summary, there are really hundreds of file formats available for standard visualization. If you want to run in parallel using parallel I/O, you really need to verify ahead of time that you can split your data in parallel. So please talk to us. We can allow for some small tests to make sure that we support parallel visualization using a parallel I/O library. Now the alternative, as we have already hinted, the alternative to parallel I/O to disk is to do in-situ visualization. And the fact is, if you have already prepared your application to do parallel I/O in the classical way, then you are nearly ready to do in-situ visualization. So there are 2 possible implementations that I will discuss this morning. The first one is ADIOS, as was presented by Samuel. So with ADIOS, just to summarize a little bit, you use the ADIOS API to write data to disk as you would do in the classical way. And then Samuel demonstrated that it's very easy with simple keyword to switch your writer engine to string data instead of writing data to disk. So from the developer's point of view, you, the person writing a simulation code, you have, of course, to adopt the ADIOS API. You need to understand this ADIOS API. The second solution, for example, as is being used in Parallel Catalyst, you need to write the so-called data adapter. So in that particular case, this is not so much, you don't have to worry so much about an I/O library API but you need to understand the VTK data structures, because the purpose of the data adapter is really to take the data from your simulation code and prepare it in a way that fits the internal data structures used by VTK for all the different mesh types which I have mentioned earlier. So the so-called VTK image data, VTK structured grid, etc. And then the process is pretty simple. Using a representative data set of your simulation, so using classical data I/O, you would prepare a data set that you would read with ParaView, with the ParaView GUI, so on your desktop, or also using a client-server parallel scenario. You would prepare a visualization pipeline. That pipeline is saved as a Python script, and then we replay the Python script during the simulation to extract data, write images, or write the data extract disk. The purpose, I mean, the big advantage of doing in-situ visualization is that, as you can imagine, instead of writing to disk a very large 3D grid, you only write the images or the result of your visualization extraction. That is usually much lighter in terms of data load. All right, so before I quit, I will attempt to run my my demonstration on Piz Daint. So what I have done is made an allocation on Piz Daint, and I'm going to run the same demonstration which Samuel has proposed, and I'm going to show you how I can include the ParaView widgets inside a Jupyter Notebook. So let me first redo, because my allocation has expired, so I need to redo it. I'll take just a second. There we go.
John, I don't know if it's on purpose, but we don't see your terminal yet.
This is on purpose. Yeah, thank you. I'm going to switch now to my browser. There we go. So I need to share my browser view, which is over here. So here you see my Jupyter Notebook. And basically, I have taken the demonstration which Samuel has prepared using the ADIOS example, the ADIOS API. And as you can see here on the left side of my screen, the same file called diffusion2d.bp.sst has been created a few seconds ago. In fact, I have launched the simulation, and the simulation is now pausing, waiting for me to pull the data. So the very first thing I do is to run my standard imports, and yes, I have imported ADIOS 2, but I have also imported here ParaView. I open my ADIOS file. Here I create a view. This is the standard visualization for ParaView in Jupyter, which we demonstrated last week in the visualization class. And I have a blank page for the moment because no data has been read. The simulation, I'm sorry, is waiting to send its first data. And then as I execute the next cell in my Jupyter Notebook here, I will have there my visualization appearing, and it's flipping between different images because as we see here in the middle of the page, I'm basically taking the NumPy array, which comes out of the ADIOS API holding the temperature data, and I'm feeding this into data structures which fit the ParaView structures. And one of those algorithms I use here is the contour algorithm, where I compute ISO contour lines at each time step. There, it's a very early demonstration. I think for sure it can be improved, but this we have proven with the example provided by Samuel with the Matplotlib animation, reading data directly from the stream, from the ADIOS stream, or the ParaView here pipeline, pulling data from the same stream. We have proven that we have now the flexibility of switching between parallel I/O to disk or parallel I/O to a stream with data consumers, which can be either a serial application, a serial visualization application running on a Jupyter notebook, or it can also be, for example, a full desktop ParaView instantiation. So that opens up, I think, the future for quite a bit of flexible I/O. All this with the facility of use of an API that is really, as Sam demonstrated, really easy to learn and to put into place. So with this, I think now you see that the visualization is not changing anymore. This is because the simulation, I see on my terminal here that the simulation has terminated. So I am sitting here on the last time step of my simulation. And with this, I also conclude my presentation, and we can open up for some questions. Thank you. I stopped sharing the screen. There we go.
Any questions from the audience? Please raise a hand.
I think we need to record, we need to remember to recall that if people are interested to go deeper into those different topics, they can always send us emails to the help desk at CSCS, and then we will address those questions perhaps in a deferred setting.
Right, John, thanks for the reminder. I would also invite those watching the video with questions to go to the user portal. Under the scientific computing, you have more documentation on I/O. We are probably going to add the link to this webinar there, and feel free to ask questions directly to us, so to Jean and to Sam. I think we can wrap up here if we don't have any other comments or outstanding questions. So I thank again John and Sam for the presentation, and thanks everyone for watching this webinar. Goodbye.